Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? First of all, hey Arya, great to have you here. um, and the plan for today, what we have on the menu is I worked on our little JSFX library off stream. I made a decision as to how the library is going to move forward in terms of memory management. I mean, the decision is not written in stone, it's not completely set, but we are going to move in this direction and we'll see how far that takes us. It may blow up as soon as we start doing real effects, or it may hold water, and that may be a good alternative, and it will be a reason for the existence of this library, because it will be unlike every other library in the sense that it will allocate memory in a way that you can have memory slots as values, if that makes sense. Now, there is some construction work going on here. The stream will be noisy. There is nothing I can do about it. You just have to live with that. Now, I guess I need to buy another computer, and to have pristine audio, I also need to move into a studio that is completely isolated. But I don't have infinite money, so here we are in a noisy environment. All right, so as I said, I made a decision. And last time, I think it was on Thursday, last week, we were at this crossroads. We could either go with the approach of using the pseudo objects in JSFX, which is the traditional approach, but they are more rigid and they lead to code that looks like this. So I'm going to open up a code that is recent and that has been written by the developers of REAPER. So I must assume that they know what they're doing. And they use pseudo objects, as one would expect, and it leads to code that reads like this. There is a lot of repetition going on here. And then code that reads like this. If you want to support multiple channels, which in this case they do support, this is the loudness meter that does LUFS and RMS computation and whatnot. Bo is here. Hey, great to have you all. Especially since I know that Air Windows is also streaming, so thanks for your business. I appreciate it. Yeah, so this is the kind of code that you have to write if you want to support multiple channels using pseudo objects. It's not the end of the world, and we could even come up with a language that would generate JSFX that would like clean this up. We would have some sort of meta language. But it would be even nicer, I think, if we could do this in JSFX itself, in the language, if we could just have a loop to deal with this kind of thing, and then for that we need real objects as opposed to these pseudo objects. So that's the direction that I'm taking. It is going to be a bit slower than the alternative. I mean, if you have like a stress test of 100 filters, it is twice as slow, and just for a single filter, it is consuming 0.1% of CPU. So it's not terrible. We'll see. Maybe we'll have to go with the traditional approach of pseudo objects, but we are going with real objects for now. And I'm going to show you what I did over the weekend. And then we are going to develop a new DSP component, a new object. We currently have the biquad filters, the low pass, high pass, and so forth using the Rbj formulas. And today we're going to implement another component, which is going to be to compute RMS. And I already have a series of videos in this channel going in depth into the mathematics of RMS and how to compute RMS in different ways. We are going to keep it simple and do a rectangular window, simple RMS computation, but efficient. I'll go into that. Right now, let's review. So first thing that changed, I'm using underscore as the prefix instead of the letter L. And I went with the letter L before because of my initial, also because it stands for library. But it so happens that in this view where Reaper shows you all the variables that have been defined and their values and the number of references to them, which is a great feature. One of the reasons why I wanted to have a JSFX library instead of just developing everything in C++ is I really like this view. And this is, as far as I can tell, ordered alphabetically, and I don't think you can even reorder this or change it in any way. And the letter L sorts in the middle, while the underscore sorts at the end. So if you have your own variables, they are going to show up here, and then there will be the library variables, the framework variables down here, and then the system variables down there. So I think that this is a nice consideration. I mean, that's the purpose of having this library. We care about those little details, and they add up. GSPT476 says, hi, hello, great to have you here. Thanks for joining us. Okay, yeah, and since I have Arya here, you asked me for a video about loops. If you're still up for that, then let me know. I know I kind of slipped on the deadline, but if you're still interested, I can record it. I just didn't do it yet. All right, so underscores and dots. You can see that I'm actually using the pseudo object notation. Actually, what I'm using is called namespacing. And before I was just using two underscores, they kind of work kind of the same, but then because I am using the underscore for the sorting situation, and because a dot is just one character while underscores are two characters, I thought I would just have a dot as the separator, and it shows up here just the same with a dot. If you don't know what namespacing even is, you don't have to worry about it. It's just a name with a dot in it. And you can think of that as part of the name of the function call. We are not using the pseudo objects feature. You're not supposed to call this using pseudo object notation. You just call this with underscore in the name, just like that. Arya says, yes, please, when you can, I will. OBS has been betraying me anyway. Sorry to hear that. OBS can be like that sometimes. And I'm finding that the core audio in macOS is also letting me down. In many cases, I have to restart core audio. I don't know if it's because I have 5 black holes going on, or if it is because of some macOS update, or because I'm using the audio interface more often. I don't know, but it stops working for no good reason, and I have to restart it, and then it gets back to working. Same with OBS. In most cases, when OBS is misbehaving, a restart works, but yeah. Okay, so the mathematical functions are kind of just the same as before, except that I removed error checking. Before, we were looking at, in fact, I spent like half an hour trying to wrap my head around the notation for ranges in mathematics. So we had checks in these definitions that would check for the domain of the function. For instance, there are some cases in which you cannot have, I cannot remember, but there are some cases in which you cannot have, you cannot compute with x equals to 0, because then you would divide by 0. And I had a check for that in the code, but that slows things down. In the effort of making everything faster, no error checking. In most situations, I'm not doing error checking. So I guess the rule is not don't run with scissors. The rule is don't trip. So you can see that now it's just the formula. I threw away the error checking. In terms of data structures, we still have the enumeration. That did not change except for the name. And we still have memory allocation, but the memory allocation is no longer setting the memory to any initial value. Again, you are only supposed to allocate memory when you are starting up the program, and in that case, the memory is guaranteed to be 0. And if you're allocating memory in some other location, for instance, you may want to allocate some memory in the slider block. If you're not interested in automating some parameter, and the parameter is going to affect the amount of memory that you need, you may need to allocate memory in the slider block. In that case, it's your responsibility to zero out the memory. I'm not going to do it for you. Making things simpler, making things faster. Then the notion of box is still there. A box is just one slot in memory, one item in memory. So I just allocate that memory, but you can see that I don't have accessors, setters, and getters for any data structure now. You're supposed to use the notation to access memory directly. So if you have a box like that, then you access its value by doing stuff like this to set and stuff like this to get. The reason why I no longer have accessors is twofold. First, I'm not doing any error checking, so it doesn't really matter. I'm not doing anything interesting in the function body. Second, as we determined last week, functions make things slower. So if we can avoid them, we will. And this kind of notation is faster than having the accessor functions that we had before. So there you have it. And then you are supposed to know that this is how you access things, and that's what documentation will be for. In fact, I actually learned something about JSFX in this process. If you want to have access to index 0, you can just do it like this, and this is also acceptable. So fun stuff. Now, for the data structures, some things changed. I'm no longer doing error checking. I'm no longer checking the bounds of the data structure to try to prevent memory accesses that are incorrect. So there is no memory safety anymore. Memory safety made things slower. So the definition of a data structure is still just a box that contains the number of fields in the data structure. Or in fact, the size that needs to be allocated for the data structure when you want to create an instance of that data structure. And the data structure is key, it's essential, it's a core feature of the library. In fact, it is what replaces the pseudo objects in most cases. So it's very important that we have this going. All right, so to define fields in the data structure C, I'm using that notation to access the number in the box, and I'm adding one to the number in the box, and then I am returning that field index. And this is how you create an instance of the data structure. It just gives me the data structure definition, which is the size of the chunk of memory that I need to allocate, and I allocate that and I return it to you. Again, no accessors, no setters and getters. You are supposed to use the struct by just using the bracket notation. Same with the box that I just explained. Then we have this special function called init. The reason why I have this is that I was not happy with the notion that my library would just overtake the initial chunk of memory that you are using, and I would allocate all my data structures, my internal data structure for the library, like undefined and errors and all the kinds of structs we need. I would just use the initial memory starting at position 0. I would use that for me. And I don't think that's ideal, because you may want to use my library with someone else's library, or for whatever reason you want to use my library, but you want to use some other section of memory that is not starting at 0. So in all those situations, I wanted to give you the possibility to go like extra advanced and set the base address of the memory that we are going to use in the library. We still have to use some memory in the library. But you can do that now by changing this and then calling init. So init is a function that you as the user of the library, you're supposed to call this on the init block to initialize the library. And when you do that, I actually start allocating stuff. So if needed, you could just, before you call init, you could like, I don't know, I think it's called next available address equals like 1,000. And then my library is going to allocate my internal data structures starting at that position. So now this library plays along with other libraries with if needed. And then in the init block, I am going to allocate the data structures I need. This function is only supposed to be called once. That's very important. And then I'm going to allocate the data structures I need, like for the bytecode filters and the Rbj filters. And for colors in the design system, colors and everything in the design system will also be values. So you can put them in arrays, you can pass them around as values. I went back and forth with this, but now that we are landing on this idea that we are doing proper objects, I'm also going to let the colors be values. That's actually kind of important, because I expect that we'll have visual components like a spectrum analyzer or an oscilloscope, things that are very useful when doing graphical user interfaces. So I think we'll have components for those things. And when we have those kinds of components, I think we need to be able to receive multiple colors as parameters, like What is the color of your background, of your axis on the graph, of your main line on the graph, and so forth. So I think it's important to have colors as values. We are going to go with that. So I need a data structure for colors. They are not just going to be a bunch of functions. And this is an example of how to define a data structure. So here we have the definition of a data structure. We use struct define for that. And then each of the fields in the data structure goes like this. And then another change is that you need to pass the name of the struct that you are allocating another field on as a parameter. Previously, what I was doing is I would just remember that you are working on this definition, and then you wouldn't have to pass this as a parameter. But I think being explicit here is actually kind of nice, except that I made it wrong, right? On this one, I had it wrong. Let's see if on this one I have it right. I think there are only 2 data structures so far. Yes, that's right. And this, yeah, all of this is correct for the bi-quiet filter, but this one is incorrect. As you can tell, I'm not done with this yet, and I haven't really ported the color situation to this new scheme. But I'm not going to do it on the stream if I can avoid it, because I don't think it's particularly entertaining. It's just what we did before, but with different variable names and slightly different notation. We'll see. And then I'm also doing that thing to initialize the Retina support. I'm forcing you into Retina support. I don't think it would be like absolutely necessary to do this now, because we can query the Retina support, and you could be explicit about this, but I think it's a good thing to support Retina, so I'm going to force you into that. Yeah, right. So that's the initialization stuff. And over here you can see that I have a struct with all the kinds of filters and all the coefficients and the samples coming in and the previous output values going out. So the same stuff we had for the filters. Nothing changed, except for the name. I'm no longer calling it the Rbj filter, I'm calling it the bi-quiet filter, which I think is a more appropriate name, though I'm still, of course, I still have references to the Rbj filter stuff in the documentation as a comment right now, but it will be a more fleshed out document later. All right, so let's see what's up. I'm going to try and make a short video to explain the concepts. Explaining it in text would be somewhat futile. Okay, I think you're talking about the script ideas that you have. And then Fotis and Stuff is here. Hey, Fotis and Stuff. Great to have you. Right, so the implementation of the Rbj filters, again, kind of the same thing, just change some variables around, nothing major. So to allocate a new bi-quiet filter, this is the data structure that is going to hold all these intermediate values that we need. We just allocate a new data structure of that kind. I'm not even sure that I want to have this kind of function. I may want to just tell people to use it like this, but I don't know. Then to configure the bi-quiet filter, we need to compute the coefficients. So you give me the filter that you are working on, then low pass, high pass, so forth. What is the frequency, the cutoff frequency, the boost frequency, or whatever, the gain. Then the width, it's no longer called wideness, which is a silly name. Width, type, and value. So type is something like, are you using Q or bandwidth or slope? And then the associated value. And then I compute all these local variables, and then this is just me copying over the Rbj formulas from the cookbook, nothing interesting going on here. Then I store, and this is the important part, I store all the values that I will need into this auxiliary data structure. You can see that I'm not storing like capital A or W0. They can be derived from the input information that I am storing. And this is so like maybe you have some block of code that is setting filters, configuring filters, and then on your graphical user interface, you want to show the filter. So you have that information available if necessary to compute the curve to actually display the filter information. So I think it's important to store the configuration, though to actually implement the filter, as you can see here in this function below, we are not using these fields in the data structure. So to reiterate, this filter is a block of memory. It's a data structure. It's a real object. This is me finding a certain field in this data structure and storing some information there for later. Then to actually filter stuff, I just need to receive the filter that you're working with and a sample. And then I'm going to extract from the filter the coefficients, as well as the previous values, including the previous outputs. Then I actually do the computation. This is the formula in the cookbook. And then I store everything for the next time you call filter. And then I have a demonstration here that is going to use the filter. Really simple stuff. I haven't imported all the graphical stuff yet, because right now the main unknown for me is whether this real objects approach is going to pan out or not. So I want to do more of the DSP stuff, more of the heavy audio processing, slow to compute stuff, and then see if it holds water or not. And that will determine some of the decisions on the graphical user interface as well. So that's why I haven't imported the graphical user interface stuff yet. But to initialize, I just need to call this init function. This is how I create a filter. Then I configure that filter with a low pass at 1000 Hertz. In this case, I don't have a dB gain because it's a low pass. And dB gain is just for peaking and shelving. And then this is my kind of bandwidth, and I have a bandwidth of 2. My kind of width is bandwidth. So this pretty much matches something that we can set on REQ, and then we can compare. Then I have this serialized stuff just to make things work. Not that we are using the number of channels right now, but we will. And then on the sample block, I am just using that filter to filter left channel, outputting to both channels. So it's a mono effect right now. And lo and behold, doing a full compile reset, and this guy works. See? We have a low-pass filter. It is working. So that's what I changed in the library. Now it's using real objects, though they are faster. As fast as I can make them, probably. This is probably the fastest you can go with real objects. All right, so let's move on and do RMS. That's the main plan for today. So the RMS computation is similar in spirit to the filter, in the sense that we are going to allocate some data structure, and then we don't need to configure RMS, I don't think. We may want to configure the RMS window, but that can complicate things. So we are going to leave that for later. Yeah. So we are going to have a simple RMS that you cannot configure. You will set the size of the window. Like, I'm going to compute the RMS for the last 5 milliseconds. And you set that window first, and then you don't touch it. You're set with that window. And if you need to change the window, you need to create a new data structure. I think that's probably not the ideal, but we'll start with that. And then you have a function that will like not filter, but it will like act on a single sample. So RMS. Yeah, for people who don't know the mathematics of RMS, go watch my video. I'm so proud of that series of videos because I had to do a lot of investigation and reading a lot of things to come up with that series of videos. And yeah, I'm not going to reiterate the whole thing, but go watch this series of videos. It is a lot of fun. I show you like why RMS, how to compute RMS, different ways of doing that. Now we are just going to implement this I guess it will be the rest of the stream, but the fastest we can. So we need to allocate some data structure. So I'm going to go here to my init block, and now there is this, I guess it's not ideal. I don't like it. How the functions for RMS need to be separated from the data structure definition. I would like to co-locate everything, but unfortunately, given the constraints of the language, I don't think that's possible. Oops, bumped into your ear, sorry. Unless... No, that's not possible. I was going to say that maybe I could have a function here like RMS init. Oh, yeah. I think that may be a good idea, actually. So the problem is that I have to define the data structures far away from where they are actually used. And that's annoying. But I can separate I can put this together into a function here, and then I call this function on the init function. And then I thought, oh, that's not going to work because my init function happens before my other functions, but I can just move it down. So I guess we are going to remove the RMS stuff. We are going to refactor this filter stuff real quick, and then we'll do RMS. It will be quick, I promise. So all I got to do is just take this data structure definition, and then move it down to where we are doing filters. So I'll do a function called filter init, and then I create my data structures there. And then I need to make sure that I will call my filter init, and then for every new component that I put in the library, I will have to remember to call the function from here, but that's all right. It's not a big deal. And then to be able to call this function that happens below, I need to transfer this to the bottom. I need to put this code here, because in JSFX, you can only call functions that have been defined above you. So I think that that amounts to the same as what I had before. And now this is, I really like this. I'm co-locating the data structure definitions with their use. I'm still complying to the expectations of the language. And this is, of course, only going to be called once, so performance is not a consideration. I like this. I'm kind of working against the grain here because in JSFX, things are kind of divided this way. In the init block, you do initialization of stuff, and then on the sample block, you use stuff. So there is already this separation from initialization and use. But it's not terrible. Yeah. I guess I could kind of work around this as well. Let's see how that would look. No. Because then on the initialize block, I would need to call a function that is defined below me. Yeah, I don't think that would work. In any case, it is all right to have this separation here, I think. But here, I think we have a better way. Collocation is a very important thing for me. So I think that everything else is about the same. I'm going to commit, but then I'm going to actually test this just to make absolutely sure that I didn't break anything. Yep, still working, just the same. That's all right. And Bo asks, are you going to include different RMS functions in the library? Well, what do you mean by different RMS functions? Do you mean the different ways to compute RMS, like what I did on my series of videos? If that's the question, then the answer is no. I'm only going to use rectangular windows for RMS. I think they are more precise, simpler to understand. They work better than approximations like exponential decays or exponentially weighted moving averages. So as far as I'm concerned, RMS, rectangular windows, simple stuff, that's what most plugins use anyway. Or I think there is a good split between rectangular windows and exponentially weighted moving averages. But if your question is, will I have different kinds of moving averages? Yeah, sure, why not? We can even implement your favorite, which is the whole moving average. All right, so now let's actually move on to the RMS stuff. I will need to have an init function to define my data structure, and I will need to call this from the init function. Then what is the data structure that I'm going to create? Well, let me first put some stuff here to help me copy and paste. Right. So I'm going to have the RMS structure, data structure. And what do I need to store? Well, I will need to store, to make this as fast as possible, I will need to store the current sum of squares. In case you don't know, RMS stands for square. So you take each sample and you square the sample. This way you get rid of negatives, but there are physical reasons why you would want to do that. Then you take the mean. So if you have you add up all these squares. So if you have like a window of 100 samples, you add up the squares of these 100 samples and you divide by 100. That's the mean. And then you take the square root. R stands for root. So you square the values to begin with. You take the square root at the end to undo the transformation. Right. So the current sum of squares is going to be another field on this data structure. And we need to have the square themselves. I guess I'll call this the sum of samples squares in samples squares. And I also need, I'm considering whether I should do the circular buffer thing now. I think I will. I have not implemented yet the circular buffer, but it will come in handy for this. And I wonder if I should implement the circular buffer and just use the sample squares as a circular buffer, or whether I should roll out a circular buffer in here to make things potentially faster, because I would reduce the number of indirections. What I mean here is I could have this as another kind of data structure that will have its own fields, and then for each computation I'm going to have to access the memory. I'll do more memory access because I will be accessing a position in memory that is actually an address to another position in memory that is an address to another position in memory, or I could just go directly and store the stuff in here. I think I'm going to try to do it with a data structure first, and if it's too slow, then we will come back to this. Now, to start one of these, I am going to create a variable called RMS that I'm going to return at the end. This RMS is going to just create a data structure based on this definition. Then I'll have a to-do here, initialize or allocate this. And that one we could set to 0 explicitly, or we could just rely on the fact that it's going to be 0 to begin with. I'm going to rely on the fact that it's going to be 0 to begin with. And I'm going to allocate this, allocate a circular buffer for that. Then we'll have an RMS. I don't know what to call this. This is the function that is going to take the sample and actually compute the RMS. I think I'm going to call this like push. I'm pushing a sample into this Not really pushing it, is it? Sample maybe? It takes an RMS and it takes a sample. I think I'm gonna call it push. I wonder what other people call this. Yeah, let's actually do this. Let's find what other people call this. So if I do an RMS, if I do a global search on my effects directory, all the effects that I have installed in Reaper, including all the repack stuff that I have installed, but just search for RMS, I'm going to find a bunch of effects that implement RMS, and some of them are going to use the pseudo objects, but you can see that, for instance, here, they have a pseudo object to pseudo method to initialize stuff and then to set the size of stuff. So maybe I can just have another to do here to remember myself that let user change window size. Oh yeah, and that's going to be important, isn't it? When I am when I'm allocating, I need the window size, and then over here I will use that window size. But I need to have a function that let the user change the window size. And then let's see what they call. They call it getL. Oh, this is a plugin developed by the developers of Reaper, so that's a good sign. And it's not too old, so that's also a good sign. So let's see what functions they have. Ah, they call it getMax. This is the function that they actually use to compute, to push a sample into RMS. I don't like that function name. Let me try to find another plugin that does this. Yeah, why not? Also developed by the developers of Reaper. Again, this getMax, not surprising since it's the same developer. This is someone else, but they're not using pseudo objects. Let's see if I have like RMS dot. And these are the plugins we looked at already, and this is me. And this is someone else. So yeah, not really. No good name for this, is there? I could probably look at Juice or whatever to find what they are using. Oh, this is another plugin. Okay, so that's not by Caucus, so they will have another name for this. Let's see the name that they use for this. They call it just RMS with some input. I was thinking about calling it that, but well, I actually want to have two functions: one to push a sample and another to cache the current RMS. Because in some situations, you just want to keep pushing samples, and then at some point in the future, you will want to compute the RMS. You want to pull out the information from the data structure. So I think I'm going to separate these into two functions. So I'll call it push now, or I'll just briefly indulge and try to find this in the Juice documentation and try to copy what they have there in case I like it. Let's see. They have no notion of circular buffers. Oh, they may have a notion of a delay line. There you go. Set delay, push sample, pop sample. So there you go. It is called push sample. All right. I'm gonna call it push as well. So what I need to do is to update both of these data structures. We'll do that in a moment, but let me react to what you all are saying. I love Burton EQ curve analyzer and I used it for 3 seconds. Seriously, where was this thing all my life? Yeah, that's a good plugin. I like it. Works very well. Right, so to push something into this data structure, I am going to access this current sums of samples, and I'm going to subtract I need to access something in this array. No, actually what I want to do is to have this in a local variable. It will be the... Why do I call it current sum of something? I'll just call it sum of samples squares and samples squares. And then I'll have a local variable with that name. And then it is going to be that minus let me see. I think I will also have the square samples or sample squares as a local variable. So this is going to become a pattern in many functions. When we use this real objects kind of thing, the first thing we have to do is to store some stuff in there, to fetch some stuff from the data structure. And then I already know that at the end of this, I'm going to need a copy of this. It's going to be very similar, except that it will be the other way around. So I'm going to fetch the values, compute their whatever I need to compute, store the values for next time. It's going to become a common pattern. So the sum of sample squares is equal to that. And then the sample squares, I think I will need some circular buffer get. And this is the circular buffer. And I want the current position. And then I will need... I think I need another variable called sample square. Which is just the square of the sample you gave me. Now that I'm thinking about this, I think I will want to extract the moving average from the R and S part of RMS, in the sense that this idea of a moving average is applicable to other things besides RMS. So this whole notion of having a circular buffer and keeping things around that way, I think I need to extract that into its own thing and then do, for instance, this squaring in the RMS stuff, but everything else in this other kind of functionality. I think it will be just literally the same data structure, but I will wrap it around with a new RMS computation kind of thing. We'll get there. For now, the sums of squares, I need to take out the thing that was there and add the sample square. And then on that position, remember that this circular buffer doesn't exist yet. I'm making it up. But on that position, I'm going to store the sample square. Oh, actually, I'll just call this like maybe push. I will push the sample square into the samples squares circular buffer. That updates everything you need. Oh, actually, this we need to update, but this we don't, because the square samples didn't change, and we already pushed the value that needs to change into the circular buffer, so that line is irrelevant. But we are going to need another function that we are going to call this like get, and I will need to receive an RMS, and I may not need any local variables for this one. This is when you have already pushed all the samples into the RMS and you want to get the RMS out. To do that, I will just take the squares and divide by the number of, or the window size. Should have stored the window size. Yeah, I'm gonna call this the window size. And then I am going to take the square root of this. So now let's work through the data structure to add this field. It is called window size. And when I'm allocating, I am going to set this field to window size, just like that. And there you have it. Maybe the window size could be part of my circular buffer, but then I would need to... No, I don't think I want that. Because later I will want to be able to change the window size. So I will have to optimistically allocate, or pessimistically actually, I will have to pessimistically allocate a circular buffer that is as big as you allow me to go, the maximum window size that the RMS computation could have. Yeah, that will be a whole thing. But for now, the window size is going to live here. Let's see what you all have to say. I'm running Burton EQ Curve Analyzer, and where on Air Windows effects, Hull is even crazier than I thought. It's the biggest Air Windows audio chainsaw, as he calls it. Chris is the serious Sam's of plugins, and Leandro is the Gordon Freeman. Okay. Okay, thanks, I guess. All right, so this is a good first sketch, but of course, we didn't implement the whole thing. So let's go ahead and implement the circular buffer, because that one is relatively easy and I think we know how to do. And I think because it's kind of a data structure, not a DSP kind of thing, I'm going to put it before the biquad filters and near data structures. This will be circular buffers. Then for circular buffers, I will need a data structure. So I'll do circular buffer init. And this is the function that I call on my init block. Just like that. Then in here, I will define a data structure and some fields on this data structure. Oh, and you can see from the name of the biquad filters that I'm expecting to have more of them. So this is actually filter biquad, but I'm expecting to have Butterworth and other fun filters as well. And I think I need to rename this to include biquad in the name. And I was using a Visual Studio Code thing that selects all occurrences of this, so it has already been renamed down here as well. Cool stuff, huh? Then this circular buffer init needs to be called down below. I already put that there. And then I'm going to rename this into the circular buffer structure. And the fields that I'm going to need are the size, the current index, and the data. There you go. These are the 3 fields I'm gonna need. Then as far as functions, I will have the circular buffer new with a size, and I will have a local variable called circular buffer. I'm going to allocate it, and then I'm going to return it. To allocate this, I am going to memory new. Is that how I'm using? Is that the name of the thing? Yes. With a size of. Oh, no. That's not how I do this. No. No, check this out. We are going to use the freaking data structure we built, right? So it goes more like this. Right, so my circular buffer is just this data structure, and then I will need to initialize the fields in the data structure, these 3 little fellows, just like that. So for the size, I just get the parameter. For the current index, I'm going to start with 0, and for the data, I am going to allocate some memory. And I will allocate size positions. Now you may, if you are paying very close attention, you may note that I'm doing something different here. Previously, I had a notion of an array, and I would use the array in here, but right now I don't have a notion of an array. I'm just allocating memory here directly. I'm saving one. When you try to push and get stuff from the circular buffer, I'm saving one memory access by doing this. It is what it is. Now, for acting on this, I'll need circular buffer push a sample into the circular buffer. And I will need some local variables. I think I'm going to need actually all these 3. So we are going to do the song and dance again. And for the, so we are pushing something into the circular buffer. I need to find a new index. Why am I calling it current index? Yeah, why am I calling stuff current underscore? I'm just going to call it index. The size, the index, and the data. All right. And because we only have a single index, right? We have the index of where we are in this circular buffer. If we had a write and a read head, then I think I would have a more expressive name than index. But for now, this is good enough. Now, let's see. We want to update the index. So I'm going to say index plus equals 1. And index equals wrap. I don't think I'm going to have a function for this. Previously, we had a function for this, but we learned that functions can be slow like that. Yeah, I think I'm going to just hard code this here. So if the index is equal to the size, then index minus equals size. So that wraps things around. Then I will go into the data. That's not how this works, is it? No, to access the data, I need to do something different. And I think that this is going to be more performance, so that's why I'm doing all this handstanding, from hard coding this here to doing this weird thing I'm about to do now. All of this, I think, will make things faster. And I don't know why I'm calling this the sample, because a circular buffer may not be necessarily for samples. It's for data in general. So I'm not going to say that this is a sample, this is just a datum. Proper Latinization of this. So this is the datum that I'm going to store in that circular buffer. Other things that I may want to store in a circular buffer, you may ask. I don't know, maybe I have a bunch of things I'm drawing on the screen and I have 5 colors that I want to cycle through. So I'll have a circular buffer of those colors, if that makes sense. I think it does. So I will just update this and then I think, now hanging there, this is going to return a position in memory for me. So my idea before was correct, and I will not save this memory allocation, or this memory access, not for now anyways. And this is more readable. Just hope it performs well enough. And then we also need to, so we already updated the data and we need to store the new index. So you can just do this line. And I think it's a nice convenience to return the datum that you gave me. And the same with the RMS computation. Not with the filter. In the filter, I need to return. This is actually wrong. In the filter, I need to return this. So right now, the filter is delaying 2 samples because I missed that one. So this should return YN on the filter. On RMS, when we push, we should, I think, return the sample. And we may not be computing the RMS of samples. We may be computing the RMS of some other thing. I don't even know what. Yeah, I think I will rename this. Not the samples squares, but the data squares. Is that right? Yeah. And then instead of sample, I'll just call this data. There you go. Then coming back to my circular buffers implementation. Let's see. And you can see that I'm here using just a conditional statement. Before, I was using a while loop. The while loop has to check this multiple times, and it is more correct. But in this particular case, I know that I will not go over more than once. So checking just once is enough. With a while loop, I'm absolutely sure that I will get the correct results, but it will check this comparison one time more than it actually strictly needs to. Okay, so this is updating the, yeah, I think that this is all right. Then I need the function to actually get from the circular buffer position. Yeah, whatever. Then I may need some of these guys. I think I will need all of them. So this is what I have now. Then my index less or equal to position, and I will need to wrap in a similar fashion to this. So if this is less than 0, plus equals size. So it wraps in the other direction. Now, you need to make sure that your position is in the range. If your position is bigger than the size, you're going to go into memory that is garbage. No memory safety. Sorry. And then I will just go to data at index and return that. Now, all of this I think makes sense, but I don't have the time to test it. So I'm going to catch up with chat. I'm going to wrap it up. And tomorrow the plan is that we are going to work on some video processors over at Arya's channel, if that's still the plan. I think it's still the plan. Stuff chainsaw, as in cutting things in a rough manner. I need to get a Burton analyzer. I've only used regular spectrogram so far. No, it's a similar joke to the programming language Perl, which is being called a Swiss Army chainsaw. Yeah, because it's very easy to cut yourself when you're using that kind of language. These are like ice baths for my brain. I hope you like ice baths. I particularly don't, but I hope you're saying that in a good and generous way. Okay, so the plan is still that we are going to work on the video processor that we began a while back. It is a video processor in Reaper that is, it's like a typewriter. Comes one character at a time. A nice little cool effect. Please let me know when you and Arya have made that Delta tutorial thing. Haha, we posted it at the same time. All right. Okay, so I think that's it for now. Thank you very much for watching. I see you again tomorrow over at IDTQD. And that is all for today. I hope you enjoyed this, and we will test this and tweak everything, make sure it works next time on Wednesday. See you tomorrow. Bye.